All right, so in this video, we're going to be looking at how to convert binary decimal numbers to binary or hexadecimal, and then how to convert binary and hexadecimal back to decimal numbers. Now, the easiest way to think about this is to remember what decimal numbers stand for. So the last number in a decimal number stands for the multiples of 10 to the 0 power. And then the second to the last digit on the second digit from the right stands for the multiples of 10 to the 1. That should be a 1. And then the third place from the right stands for multiples of 10 squared, and so on. So this number that we're starting out with, 23,721, in decimal form, this is going to represent 2 times 10 to the 1, 0, 1, 2, 3, 4 to the 4th, plus 3 times 10 cubed, plus 7 times 10 squared, plus 2 times 10 to the 1, plus 1 times 10 to the 0. Now, in binary, the base is 2, powers of 2, not 10. So just again, to sort of process the number that we're looking at, this expression right here, this would be our 2 to the 0 power, 2 to the 1, 2 squared, 2 cubed, 2 4, 2 5, 2 to the 6, 2 to the 7th, 2 to the 8th, 2 to the 9th, 2 to the 10th. So this would be 1 times 2 to the 10th plus 0 times 2 to the 9th plus 0 times 2 to the 8th plus 1 times 2 to the 7th plus 1 times 2 to the 6th plus 1 times 2 to the 5th plus 0 times 2 to the 4th plus 0 times 2 cubed plus 1 times, that should be a 3, not a 6, plus 1 times 2 squared plus 0 times 2 to the 1 plus 1 times 2 to the 0. And then in our hexadecimal form, now in hexadecimal form, we ran out of 0 through 10, 0 through 9, that's our 10 digits. So to get all of the numbers up to 16, we actually go 0 through 9 and then A, B, C, D, E, F to get to 15. So A represents 10, and B represents 11, C represents 12, D represents 13, E represents 14, and F represents 15. So this would be 11 times, in hexadecimal, 16 to the 0, 1, 2, 3, and then 3 times 16 squared times 16 squared, and then B is, sorry, this is 10, because 9 is the last decimal digit, and then A would be the first non-decimal digit. So that would be 11, and then B would be 12 times, no, sorry, 11. I'm stuck. My brain is stuck. 16 to the 1, and then 7 times 16 to the 0. Now, for converting back into decimal form, just understanding these digits is enough to figure out how to convert them back into standard decimal notation, because we just need to evaluate all of these individual places and then add them up. So for our binary case, that's equal to, now what we're going to just do is we're going to take out all the things that are 0, just to make our math a little less sort of opaque. So that one was 0. These ones were 0. This one is 0. So the zeros are obviously not contributing in any way. And then we can rewrite what we have as the decimal equivalents of these powers of 2. So 2 to the 10 is actually 1024. And 2 to the 7th is 128. And 2 to the 6th is 64. 2 to the 5th is 32. 2 squared is 4. And 2 to the 0 is 1. And so then you just go to your calculator. 1024 plus 128 plus 64 plus 32 plus 4 plus 1. And I get 1253. So that is our binary written in decimal form. Now, basically, we do the same thing for once we represent our hexadecimal number in decimal form, like so, in the place digit form. Again, our place digits here are in decimal form, and we just convert our powers of 16 to be, again, decimal form, and then we can just add them up. So this 16 to the 0 is a 1. 16 to the 1 is just 16. 16 squared is, I believe, 256. And then 16 cubed is 4096. And so then we would just add these up. And so 10 times 4096 plus 3 times 256 plus 11 times 16 plus 7 gives me 41,911. So converting out of binary or hexadecimal is straightforward. Now, how do we convert into binary and hexadecimal? So let's start with hexadecimal, because that'll actually be faster than doing binary. So if I'm trying to convert 23,721 into hexadecimal, I need to figure out what is the, so to convert to hexadecimal, what is the largest power of 16 that is still less than the number I have? So we know 16 to the 1 is 16, and 16 squared is 256, and 16 cubed is we just calculated 4,096, and 16 to the fourth is 65,536. That is bigger than the number we are trying to convert. So we don't want this one. So I'm going to strike that one out. So the 4,096 is the biggest power of 16 that is still less than our number. So what we need to do is we're going to divide by the biggest power of 16. So we're going to divide our number by 4,096 to get the whole number of times our number times it divides evenly. So if we divide 20, let's see, what was our number again? 23,721, 23,721. We're going to divide that by 4,096. We're going to get 5 and change. So 23,721 divided by 4,096 is going to be approximately 5 and change. So that we know our number is now going to be 5 times 16 cubed plus some stuff. Now, to figure out what that stuff is, we're going to need to multiply 5 times 16 cubed to see what we've accounted for. So 5 times 4,096 is 20,480. So we're going to find out what we haven't accounted for. So the difference is 23,721 minus 20,480. So 23,721 minus 20,480, we get 3,241. And so then when we repeat this process for the next digit, so now the next digit down is 256. This is bigger than 256. So we're going to take our 3,241 and we're going to divide, 3,241 divided by 256. And again, that's going to give us approximately 12 and change. So now our number is going to be another 12. So A is 10, B is 11, C is 12. Plus, well, what is 12 times 256? That is 3,072. So 3,241 minus 3,072 leaves me with 169 unaccounted for. So now I'm going to repeat my process again. 169 divided by my next digit, which is 16. That's going to give me 10 times 16 to the 1 and change. So now my number 10, remember, is A times 16 to the 1. And so now I'm going to subtract 169 minus 160, because 16 times 10 is 160. That's going to give me 9. And so my final digit, now that I'm under 16, is just 9. And so my final digit is going to be 9 times 16 to the 0. And what is that actually equal to? It's 5CA9 in hexadecimal. Now, often for these numbers, you may or may not see them written with a subscript. If they're not written with a subscript, typically we assume they're standard decimal form. So if you put a subscript under them, you're indicating that this is definitely, I mean, the A's and the C's are going to give that away, but this is definitely in hexadecimal, and not in some other form. This is more important when the numbers are smaller, like if you're in base 5 or something like that, because it could look like a base 10 system because you're using all the same numbers. You're just not using all of the numbers. All right, and then so if we want to do this same number into binary, then again, we're looking for what is the largest binary value that's power of 2 that is still less than the number that we have. So we started with 23,721. And we saw with our binary example that 2 to the 10 was 1,024. So we'll start there. 2 to the 11 is 2,048. 2 to the 12th is 4,096. 2 to the 13th is 8192, and 2 to the 14th is 16,384. 2 to the 15th is 32,768. Okay, so now this is higher than the number we have. And so we can stop here. Our final digit, if I strike that through, our final digit will be 214. So again, we can go through this process and we can, again, just divide out. Now, divide out the number. Now, the thing is, when we do binary, we actually get a little bit of a break because there's only 2 things that can happen. It either divides out 1 copy and then left over, or it doesn't divide at all. Because we only have 0 and 1 to work with. It either divides or it doesn't. So we can actually shortcut this process. If the number is smaller than what our remainder is, then we get 1 copy. And if it's not smaller, then we get 0 copies. And then we just subtract. So here, 23,000, what was our number again? 23,721 is bigger than 16,384. So we're just going to subtract 384, 23,721 minus 16,384, and we get 7,337. So we already actually know that we have 1 times 2 to the 14th. And we also know that we have 0 times 2 to the 13th because this number is already smaller than 8,192. And so if I try to divide 7,337 by a bigger number, I'm not going to get any whole numbers out of it. I'm just going to get a remainder. So now I can keep going. The 4,000 does go into this. So again, I'm just going to subtract because it can either be 1 copy or 0 copies. 7,337 minus 496 is going to be 2,341. So that's going to give me a 1. Two to the 12th. Now, 3,041 is larger than 2,048. So 3,241 minus 2,048 is going to give me 1,193. So that's going to give me another 1. And so then I'm going to take my 1193 and I'm going to subtract off my 1024. Which is going to give me 169. So my next thing I'm going to have, why did that do that? I'm going to have 1 times 2 to the 10th. Now, the next one underneath that, I will just kind of list them. 2 to the 9th is 512. And 2 to the 8th, so dividing continually by 2, is 256. And 2 to the 7th is 128. And so finally we got down to the next power of 2 smaller than our remainder. So we now have 169 minus 128. Going to be 41. So now we're up to 0 times 2 to the 9th and 0 times 2 to the 8th, but then also 1 times 2 to the 7th. Now the next power of 2 less than 41, so 2 to the 6th is 64. That's not it. 2 to the 5th is 32, so that's the one. 41 minus 32 is 9. So now we've got 0 times 2 to the 6th and 1 times 2 to the 5th. Well, 2 to the 4th is 16. That's not going to do it. 2 cubed is 8. That will work. So 9 minus 8 is 1. And then 2 squared is 4. That we won't use that. 2 to the 1 is 2. And then 2 to the 0 is 1. And so that's where the 1 is going to go. It's our last one. So finally, again, representing this in its interpretation of the binary number, we had a 0 times 2 to the 4th, but we had a 1 times 2 cubed, and then 0 times 2 squared, and a 0 times 2 to the 1, and then 1 times 2 to the 0. And so what does that do for our binary number? 1, 0, 1, 1, 1, 0, 0, 1, 0, 1, 0, 1, 0, 0, 1. Now, I will say this, when you're doing this on paper, obviously, I'm being more careful because I'm trying to explain the process. When I do this in practice, I don't necessarily write all of this out. I like keep the running tally of the number off on one side, perhaps, and then I just add ones and zeros as I go until I run out of digits. So this is not obviously, you don't really have to be quite this pedantic about all of the steps. Now, I will also say that this is not the only way to do this. You can also just go by both of these processes for both binary and hex. You can go in the other direction, but in the other direction, it requires keeping track of the remainders. So we can do that. Just as an example, again, for binary, it's easier because there's either a remainder or there's not. So if we start with the number 23,721 and we just divide by 2, question is there a remainder? If the answer is yes, if there is a remainder, so there's a decimal in the answer, then you keep the whole number and put a 1 in the digit on the right. If there is no remainder, then keep the whole number and put a 0 in the digit on the right. And then keep dividing by the base until you get no whole numbers left. Now, again, this is tricky for like base 16 because we don't really go through our lives memorizing what the remainder is in decimal form. So does anybody really remember what 3/16 is? If you do a lot of these, you will remember it. In binary, it's just a remainder. It's either a 1 or a 0, right? So it either exists or it doesn't. You place a 1 or a 0 there. If you're doing this in base 16, then you have to figure out what the remainder is. So is it 3/16? Is it 1/16? Is it 7/16? And then that's the digit that goes on the right. So it is a little easier in binary. So I'm going to do the example in binary. But if you are doing this in like hexadecimal, again, this process will work, but you do then have to figure out what that fraction is equivalent to. And so you would have to subtract off the whole number. You could use your calculator to convert it to a fraction, hopefully, and then you would know what the remainder is, and then it's the remainder that would go on that right digit. Now, for the binary, though, it's just is it or isn't it, and then you take the whole number and you continue. So 23,721 divided by 2 is 11,860.5. So I'm going to take off the remainder, and I'm going to put a 1 in that right digit. And then I'm going to divide by 2 again, and I got a whole number, so I put a 0 in that next digit. I'm going to divide by 2 again. I got a whole number. I'm going to put a 0 in that next digit. Divide by 2. I got a remainder, so I'm going to put a 1, right in front of it. And I'm going to subtract off the 0.5, and then I'm going to divide again. So divide by 2. I get a whole number, so I get a 0. And then if I divide again, I get a remainder. I get a fraction, a decimal. So I put a 1 in there, and I subtract off the 0.5, and then I divide again, and I get a 0 because I have a whole number, and I divide again, and now I have a fraction. So I put a 1, and then I subtract off the 0.5, and I divide by 2, and I get a whole number. So I put a 0, I divide by 2 again, I get another whole number. I put a 0, I divide by 2, and I get a decimal, so I put a 1 minus the 0.5, and then I divide by 2, and I get another decimal, so I put a 1, and then I divide by 2, and I get another decimal, and then I divide by 2, and I get a whole number, and then I divide again, and I just have a 1, and so I put my 1 there. When you get down to the 1, you basically just put the 1 in the last digit. So let's see, did I get the same number? 1 0 1 1 1 0 0 1 0 1 0 1. Yep, I got exactly the same number. Now, again, you can do this with the other one, 23,721. If I divide by 16, now here's the problem, again, with dividing by 16, I get a number and then 0.5625. So in binary, it's very easy. In hex, so 23,721 divided by 16, I get 1482.5625. Now, what I need to know is what that 0.5625 stands for as a remainder. So I would subtract off the 1482, and then I can convert to fraction. And that tells me that this is 1482 and 9/16. So the 9 is my remainder. That's my ones digit. That goes on the left end. And then I continue with my 1482. So 1482 divided by 16 is 92.625. Well, minus 92, convert to fraction, that is 5/8. 92 and 5/8 is equal to 92 and 10/16. So that 10, that goes in my digit, and then I continue with the 92. 92 divided by 16 92 divided by 16 is equal to 5.75. So 5, now that I'm under 16, 5 is my final digit, but minus 5, and then convert to fraction, I get 3/4, which is, if I multiply to get my common denominator, multiply by 4, I get 12/16. And so now my digits are going to be 5. Now 12, remember, A is 10, B is 11, C is 12. And then if I go back, 10 was my remainder. So A is 10. And then my first remainder was 9. And again, I get the same number that I got before. But again, the tricky part about this process, going from the remainders to get your digits, again, it took up less work because I was writing less stuff down also. But the hard part is those remainders. You have to convert those remainders. If it's binary, it's either, if there's a remainder, it's a 1, and if it's not a remainder, it's a 0. But in hexadecimal, it's almost never going to not be a remainder. And then you're going to have to figure out what that decimal is equivalent to in base 16. So you can use the convert to fraction button. You could multiply after you subtract off the whole number by 16. There's ways to do this, but both of these processes will work in terms of converting your decimal expression into either hex or binary, hexadecimal or binary. And again, every base is basically the same thing. So if you had to convert to base 8 or something like that, the process would be very similar. You'd just be working in powers of 8s, and you would be working with fractions that had, if you're doing this process, the remainders, fractions relative to 8. And the smaller the base, the easier it is because you're more familiar with those fractions: 1/4, 3/4, etc., 1/3, 1/5. I mean, those are more common, and we tend to recognize those and be able to do more of that in our head without having to think, okay, so if what is this over 16 in this case?